Now that we've started talking about orbits, and orbits being circular motion, we're going to start to bring back some other concepts that we've looked at before. We're going to start talking about energy. We've already looked at the idea of energy being mgh, but now that our value for the little g is changing and we're getting further above our planet, we can actually start using universal gravitation to start looking at gravitational potential energy as we're further and further away. So, we're going to look at a bunch of examples here. Imagine that we've a small asteroid of radius 1 meter, and this is its mass. There's a reason that this is the mass. You'll see it works out quite nicely. On the surface of the small asteroid, we place a very small and dense 1 kilogram mass. So we've got the asteroid and a 1 kilogram mass. We want to find the weight, i.e. the gravitational force of the 1 kilogram mass. So we're just going to use Fg equals gm m over r squared using our asteroid and our tiny mass. We have 6.67 times 10 to the negative 11. We have the mass of the asteroid, which was 1.49925 times 10 to the 12. The mass of the little mass is 1 kilogram, and this thing has a radius of 1 meter. And so this is very small. We can ignore the added distance there. What we're going to find here is that Fg is 100 newtons. That's a neat little result. That's why we picked the numbers the way that we did. What we can see here, though, is that because this is a 1, actually, let's say it this way. This is going to remain constant here. This is the 1 kilogram mass of the asteroid. This is the mass of, the 1 kilogram mass, the mass of the asteroid, and the universal gravitational constant. This is going to be 100 always. Here this is 1, we divided by it. We can actually rewrite the situation that's happening here as this. Fg equals 100 over r squared, because gm and m remain constant. And now we can use this expression to start to analyze what's going to happen as we start to move the 1 kilogram mass away. So imagine we start moving this thing outwards, away from the center of the small asteroid. We want to find the gravitational force at a bunch of distances, 1, 2, 3, 4, 5, 6, and 10 meters. Well, we've already sort of established a relationship here. We've got Fg equals 100 over r squared. So here at the 1 meter mark, that's the question we just figured out here. That's going to be 100 newtons. Here, it's going to be 100 over 2 squared, which is 25 newtons. Here, it's going to be 100 over 3 squared, which is 11.1 newtons, over 4 squared, let's just jump to the 5. No, let's do the 4. 100 over 4 squared is just 100 divided by 16. Is going to be 6.25 newtons. Over 5 squared is just 4 newtons. Over 6 squared is 2.7 repeating. And then over 10 squared, that's just going to give us an Fg value over here of 1, and this is all newtons. Newtons. What we can do is we can actually start to graph this, which we will on the next page here, so flip it over. We want to plot a graph of force versus distance. So at the 1 meter mark, we were up at 100 newtons. At the 2 meter mark, we were down to 25 newtons. Just want to make sure I don't screw this up. At the 2 meter mark, we were down here at 25. Is that 25? No, 25 is here. At the 3 meter mark, we were at 11.1. That's 10, 20, 30, 40, 50, yeah, so we were here. At the 4 meter mark, we're at 6.25. At the 5 meter mark, we were at 4. At the 6 meter mark, we were at 2. At the 10 meter mark, we were down here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's actually okay there. We're down here at the 1 meter mark. What we can see here happening is that this is going to keep going off, and this thing is never actually going to equal 0. There's an asymptote FG will never actually go all the way down to 0. But we had a relationship here. If you recall, the area under a force distance graph equaled work. So we can actually start to do calculations for how much work it would take to move the object while it's in a gravitational field. The only problem here is we've got something, this kind of gross curved line. So what do we do here? We can use the graph to estimate the work done in moving the 1 kilogram mass from a surface of 10 meters. Note that 1 square of the area corresponds to 10 joules worth of work. So we could theoretically count all of these things. So we got 1, 2, maybe this piece and this piece is 3, and maybe these two are 4. That's going to be 5. Maybe these two and this is 6 and 7, and then as we go off further and further and further here, we have smaller and smaller pieces, and we had some other pieces up here. I think it's fairly difficult to actually do this, the counting of this. The result that they want you to see here is that this is the work done to move it from 1 to 10 joules is approximately 90 newtons. Sorry, 90 joules. Is the result that we're trying to get you guys to see here. We're going to use calculus to prove that to you exactly. So if you've not seen calculus, or if you've not taken calculus before, this is something that I'm not going to expect you to do. This is something that you'll see when you learn it next year, assuming that next year is you're going off to university. But for those of you who have IB calculus, one of the things, or have seen calculus in IB or have taken calculus, one of the things that you know, I hope, is that the area under a curve is given or is found by taking the integral of this function between two limits. So what we can do, the function there is given by FG. So what I can do is I can take the integral from 1 to 10 of FG with respect to the radius. Basically what this means is all I'm doing here is I'm adding up all the little slices all the way along between 1 and 10 of this red area. For those of you who have not seen calculus before, that's what this operator, the integral operator, is doing. So we're going to integrate from 1 to 10 g big M little m over r squared dr. The way this integral works is that we're going to get negative gmm over r evaluated from 1 to 10. So we're going to get negative gmm, which we already established was 100. Sorry. I'll say that's going to be negative 100 over 10 minus negative 100 over 1. Again, if you don't have calculus, you've never seen this before, don't worry about it. So this is going to give us negative 100 over 10 is negative 10 minus so plus 100. We're going to see that this is the work required is exactly 90 joules, which is pretty cool. The other really interesting thing here is that this guy right here, the integral of Fg, is where we come, or is where the potential energy, gravitational potential energy comes from, negative G mm over r. If you don't know, like, if you haven't seen calculus before, that's not necessarily going to be super obvious. So regardless of whether or not you like where this came from, we are going to use it. We have to use it. And unfortunately, we're using results that I can't prove to you, that you just have to kind of accept because you don't have the mathematical skills for it. So we're just going to use this. Gravitational potential energy is no longer given by mgh. It's now given by that guy, negative gmm over r. So let's use it. So using this new potential energy, we want to find the exact value of the work done in example 1, which we have already kind of seen before, but we're going to use the work energy theorem now for this. Our initial energy plus work equals energy final. So there's some gravitational potential energy initial. We're looking for the work done to move the thing, and there's some potential energy at the end, just to move it here to 10. So we're going to get negative gmm over r initial plus work equals negative gmm over r final. So we're going to add this over. Work is going to equal negative gmm over r final plus gmm over r initial. Gmm in this case was just 100. So we're going to get the work is equal to 100 over 10, negative 100 over 10, plus 100 over 1, which we can see is 90 joules. An interesting result here, though, is if we take this thing further and we say, okay, well, what is, which is actually the example on the next page. I just want to do it, we'll just do it right here on the side just to keep it all together. What happens is if we take this guy and move him off to infinity, we move him away forever. So let's say that the radius here is infinity. We just move him as far away as we can. Take a look at what the mathematics says is going to happen here. We're just going to jump down to here. Work equals negative 100 over r final plus 100 over 1. Now if I start plugging things in here, we're going to get work equals negative 100 over infinity plus 100. Now what is negative 100 over infinity? That doesn't actually make any sense. That's not something that we can do. But if we take a look at what happens here is if we start dividing 100 by larger and larger and larger numbers, we're going to see that this approach gets really, really close to 0. So I can show you what that looks like. If I take 100 and I divide it by 100, I get 1. If I take 100, I divide it by 1,000, I get 0.1. If I take 100 and I divide it by a million, I get 1 times 10 to the negative 4, so 0.0001. As I keep dividing this further and further and further, I'm going to get closer and closer to 0.0000000000000000001. It's going to go on forever. And so the argument we can make here is that as we go to infinity, this approaches 0, so that the work done to move this object to infinity is only 10 joules more than it took to move it to 10. Which is weird, but mathematically viable. Things are getting odd. That's okay. So we had this expression before. We had mgh for potential energy. P equals mgh works for things that are close to the surface of Earth. Objects that stay close to the surface of Earth and correspond to this mg force. We have to use P equals negative gmm over r for objects that get further away. Spaceships, planets, stars, things that we can use this gmm over r squared expression for gravity for. The question that you've probably not asked is, where is the 0 for the new potential energy? For this, for the first potential energy we looked at, we said we can put 0 wherever we want. wherever makes sense, whether it's the top of the table or whether it's the bottom of the mountain, or wherever it makes mathematical sense is where we're allowed to put 0. Here, it doesn't work quite that way. And I'll show you why that is. So unlike MGH, which is 0 at ground level, this new potential energy is only 0 when the distance tends to infinity, i.e., so if I've got PE equals negative GMM over R, as R goes to infinity, this expression is going to drop to 0. So PE drops to 0, which we've kind of, is the argument that I've kind of seen already. The reason that this new potential energy here is negative, I mean, if you know calculus, we've seen already by integrating that function why this expression is negative. But if you don't know the calculus, we have to make some arguments for it. If potential energy here is 0, and it takes work to separate the masses so that they are apart, it has to start, potential energy here has to start negative to have work put in, to approach 0. I'm not sure if you understood what I just said here. So we've got potential energy plus work, and in this particular case is going to equal 0. If we're adding work, we're putting work into the system, work here is positive. For the work here to be positive and add to 0, this thing has to start negative. And so we get, for these kind of orbital problems, that potential energy equals negative GMM over R, and there's an expression on your RTZ AI. There's an expression on your formula sheet that says P equals negative GMM over R RTZAI. What that means is relative to 0 at infinity. So potential energy equals negative GMM over R for situations like this, when we're dealing with objects in orbit high above a planet. So let's take a look at this example here. What if we have a missile or a rocket? A missile is launched from the surface of Earth. Its fuel is used in an initial burst, and so it rises. So as it rises, the only force it experiences is gravity. The argument here is that here at the beginning, it fires all of its. Basically, it's not as a missile. It's effectively it's a cannon. This one massive explosion uses all the fuel at once and propels this thing upwards off the planet. So that gives us some massive initial velocity. We want to see what happens to the kinetic energy and the potential energy of this object. So as the object starts to rise, we've already seen that as the object gets further and further away, Fg is decreasing. But we know that as this thing is rising, kinetic energy also has to be decreasing, because there's a force on it pulling this thing backwards. So there's a big explosion, there's a huge amount of initial velocity, large kinetic energy to start, but Fg is pulling back on this rocket. We've got Fg backwards. We've already seen that as you get further and further away from the Earth, Fg is going to decrease, but kinetic energy is decreasing as well. Also, as you get higher and higher and higher above a surface, you have potential energy increasing. So what happens over here when R equals infinity? What happens at this point here? At this point here, we finally say that Fg is equal to 0 and potential energy equals 0. So what happens to my kinetic energy and my orbital energy? My kinetic energy is decreasing, my potential energy is increasing. That's it for today. I want you to take a look at the following questions, and then we're going to start to look at some really quite interesting applications. We're going to look at orbital mechanics in the next lesson, which will take the stuff that we've looked at in the last 2 or 3 lessons and really start to apply what it means. So I want you to look at questions 1 to 4. Is that it? And number 9 is what I want you to look at here.